because we might need some kind of data structures to perform some kind of particular action more efficiently than what other data structures can do. For example, there are some data structures that help us to access elements faster. There are others that help us to put elements in such a way that they always remain in ascending order. So each data structure has their own set of advantages, and we use those advantages to help us in competitive programming problems. So the three main data structures that we will be covering in this session, in this part of the session, are pairs, stacks, and Q and DQ. So first, let's start with pairs. So STL pairs is a data structure which combines two values which may or may not be of similar data type and stores them as a single unit. That is, uh, it treats them as a single data structure. So the unique thing about pair is that we can store two values from two different data types together. And pairs is found under utility header. If you use bits std++.h, then it includes utility header on its own. Otherwise, you need to specifically mention utility header if to use pairs. And so the way to make a pair is a pair, then data type 1, data type 2, and then pair name. And we have to close data type 1 and data type 2 uh, under these types of brackets. So and then we have to specify the data types, as this might store two different data types, and also the position of data types matter. So if we are specifying char and int, it is different from specifying int and char. So here you can see in the example, I have specified pair and then char comma int. So and then the pair name, so which is my pair. So the pair name is basically like a variable name. So if we create int x, then whatever x stores the value, so we represent that with x. Similarly, my pair can store values and we call it by my pair. So you can create any name, and then to initialize it with values. So how we initialize int x is equal to 0. Here we can't put equal to and then give it the values, but rather what we do is we specify the values in curly brackets. So for example, pair uh, char comma int, and then I have created another new pair name, my new pair, and then I have specified two things inside this, and we have to follow the semantics of whatever data type is. So for example, we specify care inside single quotes. So we have to mention single quotes there to store a care and then integer normally. So that is what we use. For accessing the elements, we use dot first and dot second. So a dot first gives us the first value and dot second gives us the second value. So for example, in this my new pair, if I do my new pair dot first, and then for example, see out my new pair dot first, then it will give me output as t. If I use see out my new pair dot second, then it will give the output as 1. So also, there are three main functions in pairs that we frequently use. These three functions are make pair, swap, and comparison operators. So the first function is make pair. So if we want to make a pair not by using curly brackets, then what we use is make pair and then give it two arguments. So how we can understand make pair function is that it takes in two arguments, and the arguments should be in the correct position. Like if we are trying to make a pair which has character first, so the first argument should be character, and then what it returns is a pair of character comma int, if that is what we specify. So this is the make pair function, like you can see below. And then we have swap. So what swap does is it swaps the content of the two pairs, like the two swaps the content of the values at two positions. And comparison operators are usually used to compare between pairs. So in integer, for example, what we usually do is, let's say we are comparing an integer which stores one value and an integer which stores two value. And if we put equal to operator, then it returns false or zero. So similarly, if both the values of pair are equal, like the first value is equal to the first value and the second value is equal to the second value, then the both of the pairs are considered same. And similarly, for all the other comparison operators, we compare the first one first, and if the first one is equal, then we look at the second one. That is what we do. So here I have given a code. So just try to tell me what the output will be, and you can scan the QR code and tell me the output. So I will wait for 1 minute. Okay, so the output for this function will be 0 and then 1. So if we put pair 1 equal to pair 2, then uh, what we will see is that since both the pairs are not equal because they have different values, so the output will be 0, which is false. Like if we try to print false, it says 0. So it will be 0. And similarly, if we put pair 1 less than pair 2, then since the first value of pair 2 is greater than the first value of pair 1, and we always compare the first element first, so it will output 1. So here is one common application of STL pairs. So uh, in this particular code, what I have done is I have tried to create a vector of pairs, and I have the values I have chosen inside the pairs are the first value represents the data it is storing, the value of the data it is storing, and the second value represents the index. Now, what is the use of creating such a vector? Let's say, for example, we are creating a vector of pairs, and what has been asked to us is to uh, return the order of indices uh, in which we have, let's say, the first value is the marks of the students. So return the order of indices in which the marks are marks are in ascending order. So what we will do is we will first store the values, like the first value will be marks, second value will be the index. Then we can sort the vector. And since the comparison happens to the first element, then the vector will also be sorted in the first element first. That means the smaller first element will come first and the larger first element will go later. And it does not depend on what is the value of the second element. And then we can print the indices in such a order that follows the order of increasing marks. So this is a common use of using vector of pairs, and there are other other uses of pairs also that I will also show in the coming slides. So this is the QR code for attendance. You can scan it, and yeah. So moving on. The next type of data structure that we have is stack. So a stack is a type of data structure which follows last in first out type of working. So and it is found inside the stack header. Like pairs was found inside utility header. Stack has its own header and it is called stack. So how we can understand stack is assume there is a container and inside that container you are putting cookies. Okay, so now and assume that the size that the cookies exactly fit inside the container. So you cannot put two cookies together in a container. So assume that in that container you have a cookie, you inserted that cookie, you have another cookie, you inserted that cookie, and now you cannot. There is no possible way you can access the cookie that you inserted first, right? Because that cookie is present under the cookie you just inserted. So the only cookie you can access is the top cookie, and similarly, you can add cookie only from the top, not from the bottom of the container. And you can also remove the cookie only from the top and not from anywhere in between or the bottom. So this is what is last in first out type of working. So the cookie that we added last can be removed first, and we cannot remove any cookie that we added before that, before removing the cookie that was just added. So this is how last in first out works. The syntax of stack is stack, then data type, and then stack name. So here you can see stack int my stack, and the way to access the element. Now here the only element we can access is the top element. We cannot access any other element. So the top element. So the way to access the top element is stack name dot top, and so here you can see that I have inserted 5 and then 6 and then 7, and then the way to and then using the dot top function I can access 7, so the output will be 7 in this case. The function to push the value inside is called push function, and here you can see a GIF in which it pushes a value, and then using the pop function it removes a value and the top changes. So after the first element is removed, the top moves down, and then we can access the next element. So functions are empty. So dot empty checks whether the stack is empty or not. If the stack is empty, then dot empty returns true. If the stack is not empty, then dot empty returns false. Size checks the size of the stack. So dot size returns how many elements are present currently. If the stack is empty, then the size will be 0. Uh, dot top returns the top element. Push val pushes the value inside the stack, and we have to be careful that the value is of the same data type. Uh, and dot pop removes the topmost element from the stack. So and also pop and push, both of these functions are void functions. That means they don't have any return value. So for this code, can you tell the output? Here's the QR code. You can scan and vote in a poll. Okay, so the output in this case will be 1, 2, and 7. So my stack.empty returns true, and true is printed as 1. And then you push in 5 and 6, and then you check the size. So the size will be 2. And after that, you push 7, and then you check the top value. So the top value will be 7. So this is a small challenge, and what we have to do is we have to modify a stack data structure in such a way that it is possible to find the smallest element in the stack in O1 time. Like we have to iterate through all the elements and then store them in such a way that the behavior of stack doesn't change. So this is a problem taken from CP algorithms, and uh, just write any approaches that you are getting in the chat. And the hint is think about pairs. Yeah, so Aditya has written an approach and it is correct. So what we can do is we can check the last value and then we can store it, and then it's not necessary to pop it, but yeah, we can check it and then change the temp variable which we have to get the minimum. So this is the code for the So this is the code for it. So what we are doing here is that, okay, so in this code, I'm finding both maximum and minimum. So I've created a stack S and I've pushed 0 and int max. Uh, this is a code only to find the maximum and minimum of positive numbers. So what I'm doing is that whenever I'm taking input, I'm just taking the maximum of s dot top dot first, that is the previous value, and x, and I'm pushing the new max and new min. Uh, so at each level, we will have what was the maximum and minimum till then. So it will be like that. Now, this might not be the best way to calculate maximum and minimum because there are other ways. There are also vectors and all. But this was just a sort of a challenge to figure out that how to calculate maximum and minimum also using stacks. So one of the takeaway tasks from this session will be reading about how we use stacks in parsing through arithmetic expressions. You can find a lot of great material on websites to read about this, and this is probably one of the best applications of stacks. So the next data structure we have is STL-Q. So a queue data structure follows the first in first out type of arrangement. So uh, it is found in queue header, like stack was found in stack header. Pairs was found in utility header. So this is found in queue header, and how queue works is what we normally think. And so how we imagine queues is there is a line for something, and they will be served like they will be served services or they will be given something. So the a person who will be coming first into the line will be served the first and then the second and then so on. So in this particular arrangement, what we see is that the element which we added the first is accessed or taken out the first. So what happened in stack was the element we are adding at last is the one we are removing first. But in this case, the element which we have added uh, at the first is the one we are removing first. So uh, you can see a GIF here in which we are uh, first this starts with an empty and then we are adding elements slowly. And then the element which we are removing first is the element which we inserted first. So the syntax for accessing queue is queue data type and then queue name. So the member functions are empty, which is similar to the empty function in stack. size, again similar to empty function in uh, again similar to size function in stack, and then swap. So what swap does is exchanges the contents between two queues of same data type. So swap function takes in two arguments, and both of them should be queues and of the same data type. Uh, then we have front. Uh, so front gives us front gives us a reference to the first element in queue. Back gives us a reference to last element in queue. So a way in which this is different from stack is that in stack we can only access the topmost element, while in queue we can access both front and back element. So and the next is push val. So it pushes a value and the pop function, which removes the element from the queue, which is the frontmost element. So this is a code, and we have q dot front, q dot back. So in this case, what we will get q as q dot front is 4, and q dot back will be 2. The next is STL DQ. So uh, DQ is double-ended queue and is a container which can work as a queue from both the directions. So we can add from both the directions, we can remove from both the directions. So a lot of functionality of DQ is similar to vectors, but it is more efficient in insertion and deletion of elements. And in fact, queues are also a bit more efficient in inserting and deleting elements compared to vectors. So if so in most of the cases, it is preferred to use vectors because it is one of the standard data structure compared to these. But sometimes using queues and dequeues can give us a much more better solution, or it can be taken as a more efficient solution because the time taken to insert and delete elements is very less compared to vectors. And so if we are writing a code in which a lot of times what we are doing is vect.erase or something like vect.clear, then queues and dequeues can be faster in those cases. So the syntax is deque, data type deque name, and the member functions of deque are exactly same as vectors. Like there is no difference between the member functions of vectors and deques, except a few differences here and there, but most of it is same. So uh, this is it for my part of the session. So the next area where you can read about stacks, queues, and dequeues is TP algorithms. And these are the two practice problems. I will give the link of them in the chat. You can access the practice problems there and practice them after the whole session gets over. And code forces is also a good practice for any type of CP problem. You can also further read priority queues, which I think will also be covered in the next part of the session. And this is the feedback, so do fill the feedback form. Uh, we can wait for 30 seconds and then move on to the next part of the session. And you can also write any doubts that you have in the chat. So yeah, prefix and postfix conversions. Yeah, so you can write any doubts that you have in the chat. And Yukash, you can proceed with the next session.
Am I audible? Can someone confirm if I'm audible? And is my screen visible? Like someone.
Yeah,
Okay, fine. So, welcome everyone for the ADaPT session 6 part 2. This is the continuation for the previous session. So, myself, Yukash Ram, and I'm a coordinator in Programming Club IIT Madras. So, I'll be continuing the STL data structures, the common data structures that are used in competitive programming. So, let's see. So before going into the data structures, I want to give an idea about what a container is. So containers in C++ are just things that are used to store data in some structured manner. Just like in real life, how we have like different containers for different things and different purposes. We have containers in C++ as well, for different containers for different purposes. So we have sequential containers, which are vectors, array, and dequeued, uh, which we saw in the earlier sessions. And we have associative containers, which include map, set, multiset, and multimap, which we'll be seeing in this session. And adaptive containers, uh, they don't store the data exactly like a container, but they are built over these sequential and associative containers. Stack and queue, which was discussed in the previous session, and priority queue, which we'll be discussing in this session. So let's see about the associative containers. One thing is like these associative containers are in the C++ standard template library. Um, so yeah. So before going into what the associative containers are, like we have to let me tell you what's the idea behind these things. Uh, First of all, accessing elements faster based on their keys rather than accessing elements based on their position. So in the sequential containers, let's say vectors or arrays, given any element, we'll be trying to access them based on their position. For example, if you want the fourth element, you can just get the fourth element by using an index or access directly like fourth element. But in these containers, we want to access the element based on their key values or based on linked with some other keys. So in these containers, we don't care about in what position they were actually included in the container. And these containers can perform operations such as searching, insertion, and deletion faster. Also, in these containers, the elements are always stored in like a predefined order. And by default, associated containers, the order is ascending order, but you can always customize it to any order, maybe descending order as well. And one more thing is these associative containers are implemented using a self-balancing binary search. So I'm not gonna explain in detail what this is, but to brief about it. So here there's this diagram. This is a self-balancing binary search tree. Uh, these are these things are called nodes, and each node has it points to another nodes, and these nodes are called the children node of these nodes. And one thing, if you notice, is that for any node in this tree, the left node is always less than this parent node, and the right node is always greater than this uh, parent node. So you can see this is the property in for that is being satisfied by every node. You can see here 80 is there, and 76, which is less than 80, but 85 here, which is greater than 80. So this is how all these associative containers are being implemented. Uh, and now I'm going to discuss the difference between associative containers and the sequential containers, so that these two containers have different properties and different implementation. So we should be aware of the differences so that we can use the correct containers in the correct problems. So the first difference is, unlike in sequential containers, elements are unindexed and cannot be accessed directly. This is one of the main disadvantage in associative containers. In sequential containers, if we need the fourth element, we can directly access the fourth element by asking for the fourth element. But in associative containers, you cannot do it directly because if you see, there is like no ordering, like no indexing in these types of containers. So suppose if you want to access the fourth element, you have to start from the first element and then access them through the iterators. Like if you want fourth element, you have to increase the iterator 4 times. So you can access only through indirectly, and the time complexity is often. While in sequential containers like vectors, this is O of 1. We can directly access. The second difference is the storage of elements. In associative containers, the elements are stored in binary fashion, which you saw here. This is the binary tree here. Unlike in linear fashion in sequential containers. And elements are always stored in predefined order, thus making it more useful in dynamic situation. So this is when you have to like sort the elements again and again. So suppose you have a set of elements and then you sort it. You add few elements, you have to sort again. So using a vector for this will be tedious because you have to sort it every time, which will not be efficient. But if you use an associative container, the elements are added in the sorted order itself uh, because the position no longer matters to us. So in those cases, associative containers will be better than sequential containers. And lastly, we have insertion and deletion of elements have binary search like implementation, thus having a better time complexity. So if you know in sequential containers, if you have to like insert an element in the middle or delete element in the middle, you have to shift all the elements in the to the right of that element to be deleted. Like you have to shift them, which is often time complexity. But in case of associative containers, this can be implemented in O of log and time complexity. So again, when the number of elements change, associative containers actually perform better than sequential containers. But if you need the position every single time, then sequential containers will be better because associative containers have no indexing. So now we move on to the data structures in C++, which are part of the associated containers. The first one is the maps. So the idea behind the maps is to store the unique key value plus. So what does this mean is that map is a container which will store values of pairs. But the catch is here is that the first element of the pair is unique, which means every time you insert a pair or any two pairs in the map, if you compare, the first element will be different. Uh, in the pair, the first element is called the key, and the second element is called as the corresponding key value. So in maps, all the keys will be distinct. So again, as in any other associative container, the values are stored in a certain order, and by default, it is in ascending order based on the key. So this is how you can initialize a map. In general, you can use map, this angular bracket. You mention the data type of the key and data type of the value, and then you give the name. So for example, you can initialize this as a string. You can initialize the key as a string data type and map to an integer type, or you can map two integers, or you can map a pair to an integer. Any possible combination will work. And sometimes you might need to initialize it in the descending order. So those times you can just add this greater in thing. This is just a comparator which tells the map that the values should be stored in the descending order. So what I mean by store in the ascending order, descending order, it means when you try to access the elements of the maps using an iterator. So if the values are stored in the ascending order, the first iterator will point to the pair which has the smallest key value. And if you initialize it in terms of descending order, then the first element will point to the pair which has a largest key value. And finally, access and search values using keys faster. which is the main point of the maps, you you assign a value to each key, and then you get the value by searching for the key. So this is the point of maps. Internally, it is implemented as same as for all associative containers. If you see here, this is how associative containers are implemented. It's the same way maps are also implemented. You can see the key values are these numbers, and the corresponding values will be these y, x, w, z. You can see the values of the left side is smaller and the right side is larger. So the entire implementation is literally the same. So let us move on. We have some basic functions in, we'll see some basic functions in map. One thing is like all these functions will be very similar in the other associative containers as well, which will be sets, multi-search and multi-map. So I'll brief through here, and in when we encounter those functions in sets and multi-sets, it will be like very easy and it'll be similar. Uh, so for inserting elements, we can insert it as a pair or insert it as two elements. So if you remember, MP4 was initialized as two integers in a descending order. So we can give the integers as the you can insert integers in pair format. So always the first element is the assumed as the key, and the next element is assumed as the corresponding key value. So this is how you can insert. So remember, inserting requires the time complexity is like O of log n. Then to access elements, maps has a neat way of accessing elements. So you can use this square brackets operator, and you can include the key value inside to assign values. So if you do this, this MP4 of 5 basically acts like a variable. So you can assign it, you can use an arithmetic operation, you can basically use like normal variable. So that's a neat part. And you can access elements in other way using this dotted function. So if you give the key value, the dotted function will return an iterator to the pair with the given key value. So one difference between these two ways of accessing the elements is that suppose if you give a key value which is not present in the map, this dotted function will give you an out of bound error. But if you try to use it as a variable, by default, all the key values, all the keys which are not present in the map has their corresponding key values assigned to the value 0 if it's an integer. So this is a neat way in terms of implementation. This will be useful. We'll be seeing in the later parts. Uh, so we have beginning and end iterators. You would have seen already in the previous sessions. So dot begin will point to the first element of the container. Dot end will point to the theoretical last element of the container, which is exactly not the last element. And a dot r begin will be pointing to the last element, and dot r end will be pointing to the theoretical first element. Uh, Most of the times we might need to access like minimum and maximum element. So since maps, sets, multi-maps and multi-sets store the elements in a predefined order, let's say ascending order or descending order, the dot begin and dot or begin can be used to access the first and last element. So which is useful. So unlike pointers, some iterators don't point to an actual element. As I said, uh, for example, dot end, they don't point to the actual last element. Instead, they point to the end of the container. So if you dereference it, they won't give you the exact value of what you're thinking. It might give you some other random value. So that's why we use dot begin and dot r begin. Dot r begin especially for the end element. So move on. So this is some a very basic code on how to iterate through the map. So we have this sum variable initialized to 0 and a product variable initialized to 1. So this is the common way of iterating to the map. So auto, auto is a keyword to assign the data type automatically based on the assigned value. So mp4.begin will return an iterator. So this is automatically initialized as an iterator. So we started the first element. If you remember, MP4 was a map in the descending order. So the first element will be pointing to the pair with the larger key value, and then we increment the iterator, so it will slowly move on to the smaller values, and then it will stop when it reaches the theoretical end of the container, which is just after the last element, which means it also includes the last element. So this is the common way to iterate through all the elements in the map. So inside the loop, we have this sum plus equals IT5, this arrow first. So IT5 is an iterator, which we know from here. So the keyword first is used to get the key, while the second denotes the corresponding key value. Note that the IT5 is an iterator and it points to a pair. So you cannot dereference it directly. So you have to use this syntax to get the first element of the pair and second element of the pair individually. So you can see this first line sum plus equals IT5 arrow first just sums up the keys, and this product thing is just multiplying the corresponding key values, and it's just the product of the key values. And one more thing, dot begin is a forward iterator, so incrementing it will move forward. So if you would have used an if you have used or dot begin, then if you increment it, it would go in the reverse way. So that's one thing you have to keep in mind. So some more functions. We have erase. You can erase by iterator. So if you give the iterator, you can erase the element by the iterator, or you can erase the element by giving the key value. Since the key value are like unique, you can just give the key value and you can erase the element from the map. You can also find the elements by key value using this dot find function. So if you give the key value as the argument, then it will return an iterator pointing to the key value if the key value is found. So there's this basic function clear all elements. You can it just removes all the elements from the map. That's dot clear. So one thing is that in the dot find function, if you give a key value which is not present in the map, then the function will return an end iterator, or it will return the theoretically lost element of the container. So this utility can be used to find whether an element is present in the map or not. So here's one application of maps as an alternative for frequency arrays. In one of the previous sessions, you have seen frequency arrays being used. But one of the disadvantages in the frequency arrays is that even though the size of the input remains same, if the values of the input are very large, let's say 10 power 8 or 10 power 9, you cannot use a vector to store that many elements, because there is a limit on how many elements you can store in a vector. So I think the limit is around 10 power 6 or 10 power 7. I don't know exactly. But if the values are like 10 power 8 or 10 power 9, you cannot store them in a vector or using a frequency arrays. But note that the number of inputs remain the same. So we can use maps here. So maps, they store unique key value pairs. So here the key can be the value of the elements, value of the inputs, and the corresponding value could be the frequency of the elements. So in this way, you can use map. So why maps will be more efficient than frequency arrays? So maps are more efficient in terms of storage because the keys which don't appear at all are actually not stored. So in a frequency array, or in a frequency array where you use vectors, sometimes in the input, the key may not be present at all, but you have to create a space for it to check if it has appeared or not. So that's the main problem with the vectors, but maps are more efficient in terms in that context. S- So they store only if the key is the key has appeared, but that doesn't stop map like that doesn't stop us from using checking whether the key is actually present or not, because by default when we saw that by default all the key values, the corresponding values are assigned to 0 when then they are not present. So this property can be used here. So whenever the key is not present, the key's frequency is automatically assigned like 0. So whenever we ask for some key which is not present in the map, the frequency 0 is returned due to the default structure of the map. So that's why maps are much better than frequency arrays. The time complexity is O log n to retrieve the frequency or the value of the like how many times it appears, compared to O of 1 in frequency arrays, which is might look like inefficient, but practically this is not a very big difference, but it provides much more utility. You can store large values as well. So here's a small problem for you guys. So here's the code. I want you guys to tell the logic and output of this code. So let me just go to this code quickly, like what it does. So we initialize a map in integer as a key as the integer data type, and the value is also integer. And we initialize a value, and we have some arbitrary array. We now iterate through the array, and for every value encountered, we increase the map value by 1. So uh, one thing to note is like since by default structure, if a key is not found, the map value is 0. So you can use this plus equal to start, even though it looked like the map, the key was not present, the map will automatically initialize its value as 0. So we iterate to this array, and every time we see we do this, and at the end, this is we iterate to the map. This is short form of short way of iterating through the map. So now here the I corresponds to the pair directly. We are not accessing using an iterator. So we are here, we are using a different syntax, dot second. This is another syntax which you can use. So we create another variable and we take the second element in each pass, and then we do this sum, and we are printing it out. So I'll give you guys 2 minutes to think about it. You guys can put the logic and output of this code in chat. So I think there's a doubt in changing the keys. Like suppose you have inserted a uh, pair, let's say 1 comma 2, and if you want to change the key value So for that, you have to go through the loop. You have to go through all the elements. If you want to change the value, then you can directly assign. You can do it in log n, because map is here, for example, here. So the map will search for keys only. It can't search through values. So to given a key, and you have to change the if you have to change the value, you can do it in log n. But like for some value, if you have to change the key, then you cannot do it in log n time. You have to like go through all the elements and check for the element which you want. Since the corresponding key values are not sorted, only the first elements are sorted. So I think that clears one of the doubts there. So I think is there any response in there? Okay, there's another doubt. Why does the iterator here doesn't require this? Uh, So this way of accessing or iterating to this, here I is not exactly an iterator. In the previous way of this, this mp4.begin will return an iterator. So this auto keyword fixes the data type of it5 as iterator. But here, this short form syntax will directly point, like directly give the path. So if you in the last session, if you've seen like in the previous session, this way of accessing the pair values was there. So here I is just a pair, but in the previous case, this it5 is an iterator, which is a pointer to the pair. So that's why you need an arrow here. While you don't need this arrow here, you can just directly use the dot to access the second element. I hope that clears the doubt. Okay, fine. I'll continue now. So yes, the answer is 5. So uh, I'll tell the logic. So the logic is just that it just counts the number of pairs of elements in the array, which such that both the numbers are equal. So you can see once the this iteration happens, the map one of the key value gets incremented every time it encounters one. So for example, in the array there are 3 ones present. So the map one value will be 3, exactly how a frequency array would work. So the same way the map is also working. So this stores the frequencies, and in the end, this is this k1 into k1 minus 1 by 2 is just the combinatorics, uh, just counting the number of pairs of elements, or n choose 2. So if you have like 3 elements, this will compute the number of ways in which we can choose 2 elements. So that's what this loop does. So the answer will be 3 plus 1 plus 0 plus 0 plus 1 is 5. So this is one of the very common types of problems you would encounter in computative programming. So that's why I wanted to show this, how you can use a frequency map instead of frequency array. Note that if you had like a very large number, let's say 10 power 6 or 10 power 7, you wouldn't be able to use a frequency array, because you can't initialize a frequency array with such a large size. So we move on to the next data structure, sets. Uh, so idea behind sets is same, but a little bit different. Here we have to store unique elements. In maps we'll be storing pair, but here just we need the unique elements. In mathematics, sets will be having no repetition, right? So it's very similar. We'll be storing unique elements. Again, the values are stored in certain order. By default, it's ascending order. Same, insert and delete elements faster and searching elements faster. So this is how you can initialize a set, set a data type and give the set's name. The data type can be anything. In some cases, you might need to initialize it in descending order. So wherever you need, you can put this greater in. This is a comparator which tells it to initialize it in the descending order. So this is how it's implemented internally. Again, the same self-balancing binary search tree. So yeah, I'm not gonna explain it. So before we move on, here's the attendance form. If you guys can scan it and fill it for the attendance. So let us continue. So again, we see some basic functions in set. As I said earlier, all the functions are very similar and they have similar utilities. Dot insert elements in it. So you can insert elements based on their data type. So you can insert pairs if it's a set of pairs. You can insert strings if it's a set of strings. Again, the time complexity is O of log n. Then we have beginning and end iterators, dot begin, dot end, dot all begin, dot all end. Same thing, similar to maps. So this is again how to the common way of iterating to the set. So this is when you have to iterate from the start to end. So set one was a normal set. So by default, the integers are stored in ascending order. So if you do this, then you will be adding the elements in from small elements to large elements. But here in the second for loop, you see, I start from or begin and we go till or end, and we increment the iterator, which means we start from the last element, it's the largest element, and then we increment in the reverse direction. So we add the elements in the reverse way. So these are two ways in which you can traverse through or iterate through the set. So there's this one application of set I want to discuss, which is the prefix mix of an array. So mix is might be a new term for most of you guys. Mix of an array of set is the smallest non-negative integer that does not belong to the array or set. So the problem is that given an array of length n comprising of non-negative integers, the values are less than 1e9, 10 power 9. So we want to compute the prefix mix of the array. So what is a prefix mix of an array? So prefix mix array itself is an array such that it satisfies this condition. So the ith element of the array P is the mix of uh, the array of elements, like only considering the first I elements. So for example, if we have an array A, which has elements as 1, 0, 2, 4, 7. So the prefix mix array will be, the first element of the prefix mix array will be 0, because considering only the first element in array A, if we have to find the smallest non-negative integer that does not belong to the array or set, we see 0 hasn't appeared yet. So the prefix mix will be 0. Similarly, if we consider the first two elements, 1 and 0, then the smallest non-negative integer that hasn't appeared yet is 2. And if we do that for 1, 0, 2, since 0, 1, 2 has appeared, then the smallest non-negative integer that hasn't appeared is 3. Similar for the other elements as well. So we have the constraints of the problem as n less than 2 into 10 power 5. Think about for a minute. Probably it would be hard. I would be discussing the implementation. I'll be discussing the solution. Any ideas? If you have any ideas, you can drop it in the chat as well. Fine, I'll explain the example once. So we have the array A, which has elements 1, 0, 2, 4, 7. So for the first element of the prefix max array P, we consider only the first element of the array A. And then we ask what is the mix of the considered elements. So P of 0 will be mix of A of 0. So A of 0 is just 1. And we have to, what is mix? Mix is the smallest non-negative integer that does not belong to the set. So if you have a set with only element 1, then the smallest non-negative integer that does not belong to the set is 0. So that's why the first element of P is 0. Similarly, for 1 comma 0, 0, 1 has appeared. The smallest non-negative integer that does not belong to the array or set is 2. Then for the third element, you consider the first three elements of the array A, 1, 0, 2, and you just check what is the smallest non-negative integer that does not belong, which is 3. And similarly, you go for, you see the 3 hasn't appeared in this set after this point. So that's why the max is like 3, 3, 3. I think that's clear. So I'll discuss the implementation part now. Uh, one thing to note is that the maximum max of any array of length n can be n. So suppose you have like an array of length 10. The maximum possible mix you can get will be 10. This can be considered by considering an array of elements like 0, 1, 2, 3 till 9. You have 10 elements. You have included all the elements from 0 to 9. So the max will be the smallest non-negative integer not in the array. So which will be 10. Now, if there was any other element than these 10 elements, then the max will be always less than 10 because you have to remove one of these smaller elements to replace the other elements. So that's why maximum max of an array of length n will always can always be n and can never be greater than this. Okay. Now, a name way will be like using a vector to store whether a number has appeared or not. But this won't be efficient because this is a prefix max. So you have to compute the max every single time. So you have to go through the vector every single time, which is not that efficient for the given constraints since it's 2 into 10 power 5 and O of n square solution would never pass. So instead, what we can do is for any point of time, the order of element doesn't matter. So we can use set here to search for the missing element faster. Or in another way, what we can do is we'll create a set with n element with numbers from 0 to n. Now what we'll do is whenever we find an element in the array, we exclude the element from the set. So the set will contain only the elements that are the possible candidates for the max. And minimum of the set would be the max. So for example, let's take this example again. We have 1, 0, 2, 4, 7. What we'll do is we'll create a set with numbers from 0 to 4. The length is 5. Uh, you can create 0 to 5 or 0 to 4, doesn't matter. Uh, no, I think we have to create till 5. Yeah, so the max can be 5. So create a set from 0 to 5. 0, 1, 2, 3, 4, 5. Now you start passing through the array. Now you see you encountered 1. So what you do is 1 can never be max of the array because 1 has appeared. So what you can do is you can remove 1 from the set and whatever is the minimum of the remaining set, that will be the max. So you had 0, 1, 2, 3, 4, 5 as your set elements. Now you remove 1. What is the minimum value? 0. So 0 is the max for now. Now, then you go to the next element. You see 0. Now you remove 0 from the set. Now, whatever is the minimum of the remaining elements, that will be the max. So you had initially 0, 1, 2, 3, 4, 5. You removed 1 and 0. Now the minimum will be 2. Similarly, the next for the next part, you remove 2, the minimum will be 3. Then you remove 4, 7, still the minimum will be 3. So by this way, you can compute the prefix mix array faster because to erase the element, the time complexity is of log n. So that makes it faster. So the overall time complexity at any point will be like the for the total will be n log n. So this is much faster. This is the code. So there is a before seeing this, there is there will be a problem set related to this topic, and the first question of this problem set will be the exact same problem. So once the session ends, I want you guys to try submitting it. Uh, I'll just go to the implementation a little bit fast. If possible, if you have time, I'll give you guys time to submit it during the session itself. So we have this, we initialize the vector, we get the input, and we initialize the prefix max array, and then we initialize a set, and then we insert elements. See, I'm inserting till n plus 1. So for safety purpose, you can insert till n as well, but I'm also inserting 0 as well. And then we go through the array, and then we erase the element which whenever we encounter. So if we encounter 1, we erase 1 from the set. So that's what I'm doing. We can erase by key value. And then the prefix mix of that at that point will be the smallest element, which can be access to the dot begin iterator. So you can dereference it directly because it points to an integer. Then you can print it out. So that's it. We move on to the multi-set and multi-maps. So idea behind multi-set and multi-maps, very similar idea set as of sets and maps. The only difference is you can just store duplicate elements in terms of multi-sets, and you can store duplicate key values in terms of multi-maps. So again, the same idea, like you can store values in a certain order. By default, it's ascending order, and you can access and search elements faster. The initialization is also pretty much the same. For multi-set, you just give the data type and name. If it were to be a multi-map, then you have to give both the data type of the key and data type of the corresponding value. Again, you can use greater in here to initialize it in the descending order. So again, we have some common functions such as insert, can insert element. For multi-set, you can insert the same element multiple times. Like if you insert twice, there will be 2 8s in the multi-set. Again, dot begin, dot r begin, everything is literally the same. Some differences will be like if you use dot erase in multi-set, it will erase all the occurrences of the given key. So if you want to erase all the eights, so for example, eights in this multi-set, you can use this to erase all the occurrences. But suppose if you have to like erase a single occurrence, you can always use this dot find to get the iterator, and then you can erase it via iterator, because iterator will be always pointing to a single element. So if you erase the iterator, only a single instance will be erased. And we have dot count function as well. This is also present in sets and maps, but it's much more useful in multi-set because sometimes you need to know how many duplicate elements are there. So if you use dot count, it will return the count of the number of duplicates you have with the same key value. But if you use it in a set or map, it will return 1 because sets and maps, they have unique key values. So if it's there, the maximum will be 1. If it's not there, it will be 0. So this is another way to check whether the map contains the map or set contains the given key. So again, as I said earlier, almost all the functions are common for map sets, multi-sets, and multi-maps. So only a little bit of variations you saw here. Similar to multi-set, there's a count function for multi-map as well to count the number of duplicate keys. And we have upper bound and lower bound, which was already discussed in one of the earlier sessions. But upper bound and lower bound is also is kind of function. It's a function in for the associative containers. So let me go through it again. So our lower bound will return an iterator pointing to the key passed in the parameter. If the key is not present, then it will return an iterator pointing to the immediate next element, which is just greater. And upper bound, it will return an iterator pointing to the immediate next element, which is just greater than key, uh, the given key. So in both the cases, if the given parameter or the key is not in the if it's exceeding the maximum value in the container, then the iterator will point to the dot and uh, the last theoretical last element of the container, which is the dot end. So both of them has the same thing. And we have the time complexity is just O of log n because binary search obviously. So we have another problem for you guys. Just let me know what will be the output of this following code. So I'll go through this code fast. We create a multi-set of with integers with name factors. We go from I equal to 1 to I into I less than equal to 64. We go through all the possible I values. And then whenever this condition is met, we just insert these two elements into the multiset. And these iterators point to the upper bound and lower bound of these key values 16 and 4. And then we get the size of the multiset also, and we are printing it. So let me know what will be the output of this code. I'll give you guys 2 minutes. Okay, fine. I'll I'll move on. So the answer is this will be the answer. This is the multi-set. So know that I and 64 by I is being put. This is just a very common way to get all the factors of 64. So these are the factors of 64. Note that the 8 will be inserted twice whenever the I equal to 8 happens. This condition will be there. So it will be inserted twice. And since it's a multi-set, so it doesn't store only the unique values. It also counts the duplicate values. So that's why the size will be 8. And upper bound. Upper bound is as we saw, upper bound returns an iterator pointing to the immediate next element, which is just greater than k. So here k is 16, and upper bound will point to the next immediate element, which is greater than 16. So it will be pointing to 32. And if we go for lower bound returns an iterator pointing to the key passed in the parameter. So it will check if it's present first. And we know from the multiset that 4 is present. So it would return 4. So I hope it's clear. And finally, we move on to this adaptive containers. And I'll be discussing priority queue. So adaptive containers not exactly like container. They don't actually store the elements. They don't. Uh, they are not like vectors, sets, or maps, but they are just a container adapter. They are built over the container like vector. And priority queue in specific is by default built over vectors. So idea behind priority queue is again the same, store values in a certain order, but here by default it is stored in descending order. And the specialization in priority queue is to access the extreme elements faster in dynamic situation. So what do I mean by this is like when there are being elements being added and deleted in the container, and you are concerned only about the extreme elements. So uh, here extreme element means if by default the extreme element means the largest element. So this is when you're adding elements and removing elements, and then you're concerned only about the maximum value of the container. So that's when priority queue will be much useful than the other containers. It's more specialized. So this is how you can initialize a priority queue. So this is data type, the container you use, and then the comparator. So the comparator is basically compares the elements. So if you want to put it in the reverse order, see by default, you can initialize it by this. It will be in descending order. Now note that this is different from sets, maps, and multi-set multi-maps. There they are stored in ascending order. If you want to initialize data type on your own, you can have priority queue of pairs, and then you can use this greater, so that this greater pair in comma int, so that you can have a priority queue of pairs where the extreme element is the minimum pair value. So by default the pairs are sorted in by their first element, which you have seen in the last session. So this priority queue will have pairs uh, with the extreme element being the pair with least first element value. The extreme element in the priority queue is also called the highest priority element. So that's why the name priority queue is the highest priority element, priority queue. So this is how it's internally implemented. If you compare it with the associative containers, these are a bit different. You can see both the elements are either larger than the parent element, or both the elements are smaller. So this is the default implementation where the extreme element is largest. And this is the default, this is when if you use greater int and the extreme element is the smallest element. So note that you cannot access any of these elements other than the top element. This is the specialization in priority queue. So you cannot access any of these elements without deleting the top element. If you have to access these elements, you have to like remove all the elements which is greater than this element in this case to access this element. So this is one specialization. So where you are not concerned about the other elements and you're concerned only about the extreme element. So priority queue, the functions in priority queue are similar to what you saw in stack, the push and pop, push to insert elements. Well, the time complexity is different because of the implementation. It's O of log n, and you have pop to remove the highest priority element. This is O of 1, which is good. And then to access the highest priority element, this is again O of 1. You can use PQ or dot top function. And sometimes you might need to get the size of the priority queue, so you can use dot size function again. This is mostly used to check if the priority queue is empty or not. And this is some additional topic which is out of our scope, but I just want to show what are all there other than the standard template library. So if you remember in the start of the session for associative containers, I was telling a disadvantage in using these because there's no way to access the elements directly. So policy-based data structures are like again data structures which are like again very specialized for some purposes. So you can guys can if you're curious, you can search it about in net. So one of the policy-based data structures is this ordered set. So I'm not gonna explain it. If you guys are interested, you can just search it. This is also rarely used in competitive programming, but can be very helpful at some time. So that's the end of this session, guys. Thank you for attending. So if you guys have missed the attendance form, you can scan it here and fill the attendance. And please fill the feedback form. It will be really helpful to improve further sessions. And if you guys have any doubts, you can put it in the chat. I'll try to make it clear. Uh, and one more announcement. Tomorrow we have a contest in the Code Forces Adapt group. Uh, so attend the contest. The contest will be counted for your certificate. So we have already mentioned it in the certificate criteria. So make sure you attend the contest. That's it, guys. Please fill the feedback form. Any other doubts you can ask? Uh, I guess there will be uh, 7 to 8 problems, I guess. I'm not sure. The problems will be kind of beginner friendly only. It won't be that much difficult on them. Probably the contest time will be like 2 hour time. It will be like a normal code forces like similar type of contest. Yeah, the contest is mandatory for the certificate. I think the contest will be open for 2 days. Uh, no, no, no. There will be also a problem set related to these topics also. So make sure you solve that also. So regarding the timing of the contest and the duration of the contest, the details will be sent in the WhatsApp group. So yeah, don't worry about like now. You will be given the details in the WhatsApp. So yeah, that's it. Any other doubts you guys can ask, or we can end the session now. Hope you guys enjoyed the session. Okay, then fine. I think there are no doubts, so we can end the session.